that would be on the topic data centers for the new age workloads. And for this, I would like to invite on stage Mr. Gopan V P, who is the GM at NVIDIA. Giving a brief introduction, Gopan is the GM for Enterprise Business in NVIDIA India and is responsible for NVIDIA's for compute and networking portfolio in the enterprise market in India. He has over 25 plus years of experience in the data center compute and networking industry. And prior to NVIDIA, he was the country manager at Mellanox India. He did a stint of a decade at Intel, where he led Intel's OCP initiative and a regional director for the data center business for Asia and later for EMEA geographies. He has also worked at various product and sales roles at Wipro and is an electronics engineer by qualification. With this, please welcome Mr. Gopan with a huge round of applause.
Long introduction for a very, very short person, right? A small guy, right? We'd like to get this started with a small video from our end. Our topic is basically on new age workloads. And what is a new age workload? We'll start with that.
I am an explorer, traveling across the Atlantic to unlock its mysteries, and back in time to understand the origins of the universe. I am a visionary, bringing sharper focus to researchers, and brilliant clarity to surgeons. I am a healer, making treatments as unique as every patient, and giving new life the chance to thrive. I am a guardian, looking out for dangers around us. And in the depths below. I am a helper, enabling healthier, more sustainable crops. Bringing them to market faster and preparing them for the table. I am a creator, building virtual worlds to help robots learn faster and make our connections stronger. I am even an avatar, and you can ask me any question.
Who made this song?
Ava used artificial intelligence to write this song, and it was recorded by the London Symphony Orchestra. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere.
Even the music was composed by AI. Now, this is a worldwide scenario. Now, let's come into looking at the Indian scenario and how we see workloads emerging, evolving, as Subbu was saying, and how the data centers should actually cope up to the new age workloads. That's basically the scope of this quick presentation. I've got slides, plenty of them. I think I'm overdoing slides for this. I'll try to skim over a few of them quickly. Now, we talked about AI. This is all pervasive. That's a given. The next, couple of decades is going to be AI age for sure. Just take up a couple of use cases in the country itself, like telco, 400 million subscribers. Got contact centers, people are talking about 5 million calls per day. Now you want to do a sentiment analysis of a particular program you launched from the calls. Do you think people can sit back and just do an analysis of this? Absolutely not possible. Definitely need artificial intelligence in the back end to work it out. You take a short video platform, let's say, you know, ShareChat, Daily Hunt, TikTok, many of them. You got, what, 10 seconds? That's the attention span of a person. Within the 10 seconds, you need to lead him to the next recommended video, which he has to watch. Otherwise, you lose him. Near real-time kind of recommendation is what typically is needed. So you take this to multiple other use cases here. You take fraud, you take e-tail, you know, anything. You take automatic, let's say, speech recognition, text to speech. Anything, you need a big AI engine at the back end. Now, if you look at the enterprises that we are looking at AI, there is a Deloitte research which is done, which said 67% of enterprises worldwide have already put up some kind of ML in their enterprise. 60% of them are already using AI in their enterprise softwares, knowing or unknowingly, whichever way it is. 97% of them are saying that they will adopt AI by next year. This is a 2021 research, by next year, which is maybe by 2022. So it's a clear given. Knowingly or unknowingly, you are embedding AI in your enterprises, and that is a need of the hour. That's a way to go also. Now, you flip this around. What are the issues which an enterprise sees? Definitely, there is a lot of investment. You know, Subbu was talking about capital. Capital is definitely expensive. Now, you look at the developer, the skill set, the productivity of the developer is very critical for any enterprise today. Now, there are two things which constrain the developer. One is skill set, the kind of resources which is available for him, from maybe in terms of compute cycles. Like AI needs, let's say for a training algorithm which has to be run, it needs a heavy backend infrastructure. And this is an iterative process, and it has to be run for, let's say, months together, or weeks together, days together, you know, get a training output done. So for that, compute cycles are at, scarce today, and that's a constraint for the developer. Oh, sorry. Now, the last part here is in terms of the way enterprises are organized today. You've got a data sciences team. Typically, the data sciences team is away. It's a completely different team altogether from the IT. So this is actually two disjointed, systems in the company which is trying to work together. So these are clearly the problems the enterprises face. Now, let's look at it from an IT perspective. Resource demands. Like when it comes to AI, the compute requirement which is needed is absolutely crazy. Now, earlier you had the leeway of driving a lot of these programs on a typical CPU which does sequential processing. When it comes to artificial intelligence or any of these new age workloads, let's forget for that matter artificial intelligence as a use case alone. You take anything else related to data, analytics, you take high performance computing, you take genomics, any of this kind of applications, it's a very parallelized kind of algorithms which you get, programs which you get, and parallel processing is a need of the hour. So a sequential processing which is done by the yesteryears, or the CPUs has to change to a completely parallelized kind of infrastructure, a compute infrastructure, which can deliver the kind of performance needed for the day. Now, typically most of you are used to cloud native applications. Most of them are cloud native. You typically talk about microservices which can be spun up in a virtualized infrastructure. And they actually, this is spun up as in when you need it, and they need to work with a multi-node kind of an environment. There is a real large requirement for high throughput, low latency performance on the network side also. Typically, you take up, we were actually having a conversation with Rajesh earlier. He was talking about AI workloads which he's trying to deploy. He was clearly saying that network bandwidth, network is a very typical consideration. Now, network comes in multiple ways here. Like you have a, let's say one compute unit. You can have a system with multiple computes. Like let's say you have SMP, like the multiple processors in a same server, which has to be interconnected. Now this has to be interconnected with I/O. Let's say it used to be done with a PCI Express. That's the way typical architectures were earlier. Now it has to give way to newer generations, like PCI Express, which is running at around 100 Mbps kind of throughput, 100 Gbps kind of throughput, has to move away to let's say, new systems which can deliver 9 times, 10 times of that kind of throughput. That's network throughput within the system. Go outside the system, you're putting up a multi-node kind of an environment, multiple servers in a system. You need a high performance, low bandwidth, low latency kind of a performance fabric to interconnect these systems together. The need for networking. Finally, you typically look at the way these kind of workloads are implemented. I mean, anybody from the IT side, the CIO side here will know, typically a data scientist will come and ask for a particular workload to be deployed. He'll say, just let's put up a small cluster and drive it. This is for your specialized application, clearly creating silos. That's the way it is run today. Now this has to change. Now this has to change. This is the way it typically looks like. Now you have a typical data center which has got the traditional enterprise application. Most of this are virtualized. You get optimal usage of resources with virtualization, and this is typically where your the complete compute based on CPUs are run. When it comes to the new age workloads, you take up an AI workload, take up a data warehousing workload, take up AI training, inference, whichever it is. You typically get this run in a small cluster, which is creating a silo. Now, for ones and twos of applications, this is certainly an architecture which is possible. You can still run it. But the more and more you start deploying such workloads, this is certainly not a possibility. You have to move away to a completely, a single unified kind of a data center infrastructure, which is completely virtualized, and the consumption can be based on the usage. Now, if you need a CPU kind of a compute, a person can be sliced, given a instance of a CPU compute. If you need a high performance parallelized kind of a GPU workload, you can actually give a slice of that. You have to slice and dice it the way you want it, the way the microservices which is spinning up or ramping up needs from the data center. So it has to be a completely unified data center. Now, the way we look at data center, this is the way our outlook is. Typically, the earlier unit of compute for the data center, for your compute requirement, for any enterprises, was this server. Typically run with the CPU, which is a central compute, and that's where all your applications or apps used to run on the CPU itself. Typically sequential processing. That's not an architecture which is possible today. Now you have a completely virtualized kind of infrastructure where you have 3 kinds of compute which we see. Certainly goes without saying the CPU is a central core of the architecture. Now, when it comes to specialized high performance kind of workloads, parallelized kind of workloads, you certainly need a GPU, which can deliver the compute requirements of today's applications, the new workloads of today. Now, when it comes to the networking, you need there also a new architecture, which can give you a very low latency, high performance kind of a network throughput. So this put together is a complete architecture which you're bringing together, and that's how we see it. The data center itself, not the server, the data center itself is a clear unit of compute going forward. The server is just, is just one unit which adds to this compute pool in the data center. This is the way we see the architecture, and we'll go through each one of them just to go through quickly. Now, in terms of GPUs, I hope all of you know what a GPU is. Anybody? I hope all of you know what a GPU is. What's a GPU? Right? So what started off as a unit of compute or a compute unit for graphic applications, typically gaming, visualization kind of applications, is moved over to a data center kind of a compute product. So on the left side, what you see is this is a complete data center offering from NVIDIA. On the left side, you see most of them are compute units, which has got graphics capabilities also built in. But once you move to the right side, clearly the enterprise, like let's say an AI training kind of a workload which you want to run. I was talking about speech as a use case earlier. Typically to train a particular language, let's say Hindi, for a telecom kind of a use case, one language, just the training on a basic data set, one of the companies here used to take around 45 days on a small cluster of, x86 based compute system infrastructure. With just moving over to a 800 based infrastructure, it is clearly cut down to, right now we are talking about around 3 days, 45 to 3. So you look at, I was talking about developer productivity earlier. So you look at a developer who's come out with a model for AI. He's trying to train a speech workload, a speech model on AI based on a data set. Currently it's taking, earlier it was taking around 45 days. So 45 days he actually waits for the output to come out. Now you look at it, by shifting over to a new compute infrastructure, he cutting it down like what, 1/9, 1/10? And that's the kind of performance improvements which you're talking about. That's the kind of requirements you're talking about. That's what is getting delivered by these kind of compute units. So this caters to a workload across, starting from VDI. Subbu was talking about VDI as a requirement. Like you have a virtual workstation, you have virtual HPC, and any kind of workloads can be done with this kind of infrastructure. Now, this is this complete range is based on what we call as the Ampere series of processors from NVIDIA. We have just announced the latest one, which is called a Hopper. This actually compared to the earlier generation, like the A100 series. This product is almost like around 3 to 4 times the performance on standard floating point instructions. Almost around 8 to 10 times the performance when it comes to specific instructions like DPX-based instruction, which is used for route optimization, genomics, and those kind of workloads. 8 to 10 kind of 10x kind of performance improvement. Now you look at the way the industry is. You would have all heard of Moore's law, right? Moore's law talks about doubling. I used to work for Intel. I know what Moore's law is, and been a proponent of Moore's law for ages. But Moore's law talks about doubling the performance in 1.5 years. That's the way it was. A100 to H100 is just not even 2 years. We are talking about generic throughput, performance improvements of around 3x, but specialized codes going up to around 9, 10x. Compared to a standard CPU, 40 times better in terms of for certain workload performances. Now, there is another perspective of it. Now, you look at the way a CPU connects to a GPU in a system. Typically, the connectivity is based on PCI Express, right? The CPU does scalar kind of processing. Typically, when it comes to vector processing or the AI kind of processing, it is typically done on the GPU. This has to be interconnected also very closely together, which used to happen with the typical PCI Express, which I said earlier is a very low performance kind of bus to interconnect. One of the primary reasons why we are actually going ahead and launching this product, which is called Grace, a CPU, which does, it's a high performance CPU based on ARM core. Around 144 ARM cores built in within the same CPU, connecting to the GPUs with a very, very high performance bus. 900 Gbps is the kind of throughput of this bus, interconnecting the CPU and the GPU. Now the scalar architecture and the vector architecture is very closely bound together with a very, very high speed kind of bus within the server. And that's what is typically needed for these kind of workloads. And most of this is actually happening not just outside of India. A lot of this is actually right now happening in the country with a lot of adoption of even Hopper and even Grace requirements coming up. Grace actually is a product which will be available only in first half of next year. But even now, there are a lot of requirements. Actually, we are talking to customers for these kind of CPU, GPU kind of combinations. So this is a reality. This is the way the data centers have to change. The compute has to change the data center. Now just look at, let's look at, for 1 second, let's look at, or 10 seconds, let's look at the networking part of it. So network and network I/O is a very, very critical piece of any infrastructure. Like let's take telecom. Like I/O is a very, very critical requirement for them. You take up, let's say a data center, a large data center, east-west traffic is a very, very critical piece of it. East-west is within the data center. Now, the way the implementations were earlier, a lot of these network functions used to be, running on the server CPU itself. Now, the server CPU is a general purpose CPU. It's not a network related CPU, right? So it's not ideally suited to run network applications, network functions. Now, what we are actually trying to do is, we are trying to offload a lot of this network functions, which is related to, SDS, software-defined storage, software-defined networking, a whole lot of this onto the NIC. Now, earlier we used to have a standard NIC, but now it's evolving to a completely intelligent, bootable kind of a product, bootable kind of a CPU, which is called a data processing unit, which can offload a significant portion of the network functions. Like, let's say you're running VMware. A lot of you are used to EGX, right? What if I come back and tell you, and if you run EGX, definitely there is an overhead on the server for sure. EGX has to run on the server CPU. The VMware EGX has to run on the server CPU, right? It definitely takes a bit of the server CPU for sure. So what if I come back and tell you that the EGX layer can be run on the network card, which is a DPU. So you're freeing up CPU cycles significantly. Now you look at a server, the most critical component, the most costly component on a let's say, I'm just putting a ballpark numbers here, on $10,000 box, which is a server, the most critical component is the CPU. Typically it takes around $5,000, $6,000 for the CPU, 2 sockets, right? Now, what if I come back and tell you that I can offload 35% of the load, the workload, from the CPU onto the NIC? That's TCO in the data center. Like, earlier we were talking about hyperscalers. Now, hyperscalers are able to offer this kind of optimization based on these kind of offload technologies. Now, 2 things happen. One, you free up CPU utilization. CPU load can be put onto the NIC, that's number 1. Beyond it, this is a product which is ideally designed to run network workloads, network I/O. The network runs at line rate throughput. So if it's a 100G network or 400G networks, it works at 100G, 97, 98 Gbps is the kind of throughput which you get. You will not get it in any other way. DPU, the next pillar of the data center in terms of compute, when it comes to I/O compute. Now, the other bigger problem which we said you're creating silos, maybe as clusters in the company. The other bigger problem for typical AI kind of or new age kind of workloads is people depend on open source. Definitely, that's the ideal way to go when open source is the right way to consume technology. The problem when it comes to AI is you don't know where to pick and choose the open source softwares from. So what we have done is we've actually put a thought together. We've put up a complete open source repository of applications or application stacks specific to areas, domains, in which is freely downloadable to you. Like, for example, we were talking about speech. Speech has got something called Riva or NeMo. Like if it's a speech training which has to be done, we can actually do it on a software stack called NeMo, which runs in the backend. This is once again open source, guys. Now, how do we work it all together? This is the way we see the whole thing. We are a complete stack company, solution stack company. We are a full stack company, not a solution stack. We are a full stack company. We provide it, end to end, but we don't provide a solution. That's what NVIDIA does. Now you start up from the bottom layer. You have the compute layers here: GPU, DPU, and the CPU. All the 3 put together. You got platforms which are available from NVIDIA as well as partners to consume these technologies. You got acceleration libraries which are available from our end, which accelerates the whole thing, which is based on some technology called CUDA, which is a SDK library set. And on top of it, you got a complete application framework, like recommendation systems I'm talking about earlier. Recommendation systems use typically a product called a stack called Merlin from our end, which drives it. Now, autonomous driving, almost 34 of the world's OEMs, the car OEMs who are actually doing autonomous driving, have adopted NVIDIA, what is called the Drive platform. So this is a complete set of stacks which are available from our end. Now, for you, as a data center provider, as a consumer of technology, as an enterprise, how do you do it? All of this software is right now available as freely downloadable containers from what we call as NGC, NVIDIA Graphics Cloud, Graphic Cloud, GPU Cloud, from where you can freely download it and use it based on your requirement. If you want to run it and test it out, there is something called a launchpad also which goes beyond it. You can actually, for a limited time, you can actually put it on launchpad and test it out. Now, in terms of systems are available from NVIDIA. This is a system, very, very high performance training kind of a system which is available directly from our end called DGX. Now, you needn't pick up a system from NVIDIA. You are free to consume it from wherever you want it. You can take it from a cloud service provider. All of the large cloud service providers, even the CSPs in the country, offer NVIDIA-based compute platforms. Now, it's available from all of the OEMs also. You go to Dell, HP, you get NVIDIA certified systems which can run on a lot of these technologies on top of it, all certified from our end. So the way you typically consume technology from NVIDIA. Now, finally, if you look at it, these workloads are a reality today. You can deny it only for so long. This is clearly the reality. Everybody is adopting it, knowingly, unknowingly. You need to put up a data center infrastructure at the back end, a completely virtualized one, a seamless one, which can take care of these workloads also, for which these components are very, very critical. From generation to generation, we have actually been providing significant cost savings, or TCO savings on these products which we bring to the table. The way we work is we are actually working the stack and the infrastructure together. So it's a fully optimized kind of a stack which you get, which you can build on top of. And that's where the TCO and the benefits, what we are talking about, comes to you. Finally, it's a completely scalable kind of an infrastructure which you can drive, because your need on these workloads definitely are going to scale. That's also a given. So when you put up an infrastructure, it has to be a scalable infrastructure. If you put it up on a completely virtualized infra at the back end in the data center, with these three elements taken care of, like the CPU, GPU, and the DPU, which are the compute elements, and the stack which you build on for your applications, that's the way your data center should scale. And that's the only way you can actually future protect or address your future needs on your data center which you're putting together. Sorry. Pardon? Data processing unit. Yeah. Yes. So these are three processing units. It's basically a CPU itself, GPU, CPU, and the DPU. These are three processing units from our end. DPU is for the IO, GPU for these workloads, and CPU will be, at times it could even be the administrator of these workloads being passed between. Pardon? Scalar data processing will happen on the CPU for sure, whereas a vector parallel processing will happen on the GPU. That's the way that 100% parallel. We are talking about in a typical GPU, like number of cores which you find in a x86 CPU look like what? Like AMD, Intel, whichever it is. We're talking about sub 100. We are talking about smaller cores here with a GPU, goes to around 12,000 cores. So it's much more smaller, but it's an iterative process which has to be spread out and done. That's a parallel processing architecture which we're talking about. Right? And these kind of workloads can be done only on that. That's also a given. I'm there. Yeah, so this is it from my end. Just wanted to give you a glimpse of how this is changing, how the data center should be to cater to these workloads, and that's a way you should go forward. The industry should go forward.
How are you dealing with the
Absolutely. I mean, that's once again also a reality, goes without saying. We've been managing pretty nicely till date, because NVIDIA works very closely with one of the largest semiconductor manufacturing providers, basically a Taiwanese company, very closely work with them. We've been hit, but not been that bad. On the compute side, we've actually been managing very well in the sense of the GPU portion of it. The biggest portion where we hit is on the networking side, and the networking industry is the most hit when it comes to supply constraints on the semiconductor side. That's where we are more impacted than with. We've not had too much of issues as far as catering to demand in the country with this crisis in the last 1.5 years, except for networking. That's it from my end. Any questions? I'm also available, or if you got time for a question or two. No. So either it was a good job or a pretty bad job. I take it as a good job. Yeah. Thank you.